time is 17 o'clock.
Thank you very much. Good morning, everybody. Just a reminder, Friday, March 7, not this Friday, but the next Friday, Friday, March 7, from 6 to 8. And the place will be announced. As soon as I get the room reservation, I will let you. Okay, good. Now, let's continue our discussion. We wrap up the material on the call today. We started looking at the end-to-end mechanisms. This is end-to-end mechanism. What we have been so far is the network-based mechanisms. This one is end-to-end mechanisms, which is the TCP, the Transmission Control Protocol. And again, as I told you, Transmission Control Protocol is a reliable connection-oriented, provides for both flow control and congestion control. In the case we are talking about the problem that the receiver buffer is going to be what? Filled up. So the receiver is going to tell the sender how much space does it have through the window, which is called the receiver window size, explicitly. The receiver window size indicates the number of bytes that the receiver is willing to accept. Sender send a segment in a packet. When the receiver receives that segment needs to be, keep in mind, the acknowledgement could be piggybacked with the segments that the receiver is sending back to the sender, or directly as an acknowledgement if the receiver does not have a segment of its own. And there is, again, as I told you, if you look at the receiver, the buffer, this is the receiver buffer. This is what? This IP data in the buffer. This is what? These are the bytes that have been received, that acknowledged, but they have not been what? Read by the application yet. The application happens to be a little bit. So these bytes have been received, and they have already been what? Acknowledged. Acknowledged. This is how much space is left. This much is going to be advertised in this field, in this window size. When the receiver window size, when the sender receives that acknowledgement, he adjusts his window based on what? Based on the following equation. So the sender window size is less than receiver window, open a bracket, the last byte. Where are we talking about? At the sender side. At the sender side. The last byte sent minus acknowledged. Last byte sent minus the last byte acknowledged. What is this? In between the brackets, what does it represent? The last byte sent minus the last byte acknowledged. What is it representing? This is representing bytes the sender send but have not been what? Acknowledged yet, which means we're still in the pipe. Are you following on that? They are still in the pipe. What does that mean? Let's assume the receiver is telling you that size is 50 bytes. And let's assume that you have already sent 50 which are not yet acknowledged, which means they are what? In the pipe. And the receiver has not received them. The receiver would have acknowledged them. The receiver has not received them, but you have already what? Sent them. Send more. You can send 35. You cannot send more than 35. Did you understand or not? The receiver is telling I have a space for what? 50 bytes, and you already know that you have sent what? 15, which is not yet acknowledged. Yes? Left. You have left a space for what? 35. So, one more time. Is the receiver advertised window minus The minus the last byte acknowledged. The difference between these two should not exceed what? Or should be window size. Sender window size means what? How many bytes can the sender still send before it has to stop? It has to stop because it has reached the what? The limit. Clear? Clear? Now, keep in mind that when a flow control is used, automatically a little bit on what? Congestion also. So even though the purpose of the flow control is not to over receiver with more traffic that it can handle, but at the same time you are relieving the what? Because these segments or these packets will go through the network. So if you slow down, the network also will be what? Clear? Oh. This is the equation that I just, this is at the receiver. How much is the advertised window? The advertised window is what? Is the receiver buffer size, which is from here to this. The last byte received is this one, minus the last byte by the application, which is this one. The remaining is the what? Is the receiver buffer size. Clear? Receiver buffer size reaches 0, what does the sender needs to do? When the receiver window size reaches 0, what does the sender do? To what? To stop. You cannot transmit anymore. Clear? Until the receiver tells you what? It's now you can what? Now you can open. By the way, if this receiver does not tell the sender can open, the sender will probe the receiver periodically, tell him what is happening. Did you have a space for me? Are you following me or not? It's up to the receiver to respond to that. That flow control. If the receiver wants to control the rate at which the sender is sending, then it will what? Delay the sender cannot open his window. The mechanism, we called it what? The sliding window algorithm. We already talked about this in 450. This is just a quick review for it. Looked at a situation why TCP fails to provide for higher efficiency in the case what? A long fat network. When you see long fat network, what does it mean? Long in the sense that the delay is high, and fat in what sense? In the sense that it has a large, that means what? The bandwidth delay product is what? Is large. Bandwidth delay product, we define in 450 the bandwidth delay product. The bandwidth delay product, which is measured in bits, is the max that you can insert onto the link in a given interval of time. That given interval of time is regarded as what? RTT, one RTT, which means what? It means that during this RTT, this is the RTT, during this RTT, how many what? How many bits can you transmit? How many bits can you transmit before you reach the limit? Before you reach, of course, is set by the what? By the bandwidth. So we took a numerical example, this is quickly from last time. We have a link, end-to-end link of 128 millisecond, which means the round trip is what? Double that. And the bandwidth happens to be what? 155 megabits per second. This is what we refer to it shortly as what? OC3. OC3, it stands for what? Optical carrier level 3. Notice, by the way, this is not relatively extremely high. It's high, but extremely high, 155 megabits per second. Okay, now what did we calculate product? If you multiply 155, in other words, 155 mega times 256 milli divided by 8, because I want everything in terms of, I ended up with what? I ended up with roughly 5 megabyte. What does that mean? It's 4.85 megabyte. What does it mean? 5 megabyte. What does it mean? It means that the sender can up to 5 megabyte before it exceeds the bandwidth of what? Of the bandwidth of the link. It can send 5 megabyte. However, if you look at the header of the TCP, which is the following. This receiver window size from here to here is 16-bit long. This is 16-bit long. The maximum receiver window size is 2 to the what? 16 bytes. It's roughly what? 65,000 and change. 536 bytes. Then go. It's 16-bit, but the unit is in what? In bytes, which means what? Send at most this amount of bytes. How much can he send over this link? how much theoretic? He can send 5 megabytes, but he can only send what? Roughly what? A kilobyte, 64 or 65. Are you following on now? For an efficiency of how much? Efficiency or length is roughly 64K divided by what? 5 meg. Are you following me or not? The link utilization is a percentage times what? 100%. Okay, what is this? It's roughly 12, so it's what? It's roughly 1. It's anyway. It's terrible. Forget about the number. Do you agree? Okay. So what did they add? I added in TCP in the option field. There is what is known as what? A scalar multiplier or a scalar factor. Scalar factor in the option field. In this option field, during the call setup, during the handshaking, the client tell the server, can we agree on a scale? Where am I going? Who's I? The client. Where I am going to what? Multiply whatever by that scaling factor. Let's assume, for example, the scaling factor is what? Is 4. Just an example. It means if the maximum is 64K, the sender can send how many? Scaling factor of 4, which means what? Multiply this by what? By 4. Clear? At that time, the handshaking, the server may what? May or may not agree on this. May or may not agree. Agrees on this, then during the session, whatever it is here will be multi-scaling factor. Did you get this or not? Did you get this or not? By the way, did the efficiency, did the link utilization, and instead of what? And instead of this one, 64K, it will be what? 256K. Utilization improved by how much? 4 times. It's still not good enough, but it improved by what? It improved by some. Clear? The scaling factor, by the way, that scaling factor I'm telling you about does not exceed what? 2 to the 14. Why? Because the sequence number from here to is how many bits? This is 32 bits. With this 32, 2 to the what? 2 to the 32. If this one is already what? 2 to the 16, one should not be what? Should not exceed what? Roughly to what? 2 to the 14. So that the price to the what? To the entire range of the what? Of the sequence number. You cannot use the sequence number before it get what? Acknowledged. Before it get acknowledged, you cannot reuse those sequence numbers. Clear? Oh, that's the flow control. Now, the congestion control. Again, we talked about this, but just to make sure, because some of you might not have taken the class with me, just to make sure that we are on the same page. Okay, congestion control. First of all, what is congestion? One more time. The buffers in the router, in the network, get what? Get piled up, and the router starts what? Dropping the packets. TCP opted for the following strategy. Look at the strategy of TCP. TCP strategy, going to what? I'm going to aggressively increase my rate of transmission until what? Can do occur. In other words, I want it to occur. That's the strategy of TCP. Do you follow me or not? Even though, as we will see, it's actually startling, but it's just a little bit misnomer to say what he is doing slowly. Just at the beginning, we will see that in just a second. Clear so far? Once TCP does not depend on the network to tell it that congestion has occurred. In other words, he is using a strategy which is what? Implicit, not explicit. In some other technologies that last time, there's one which is called the deckbed, in which the routers inside the network will insert header of each packet telling what? When it perceives that congestion is what? Is that when the receiver receives that packet with a bit, it will what? In the acknowledgement of the other side, will inform the other side to what? To slow down. Are you following? Because it tells him what? It tells him that, telling me that congestion is about to what? Is about to occur. Clear? This is called what? Network assisted control. Network assisted congestion control. TCP by itself is a what? Is a congestion control. No explicit feedback from the what? Network. The sender needs to perceive of the network itself through what? Through mechanisms. One of them is called the timeout mechanism. Every time, that's an indication that the network is what? Congested. Let's see if here's the second condition. The second condition is when the sender receives multiple acknowledgements. Duplicate acknowledgement is an indication that the receiver is receiving segments that are what? Out of order. Segments that are what? Out of order. I will show you that in just a second. Okay. As again, we have taken this all in 450. As I'm going to go a little bit quicker. We at last time at what? At the relationship between the offered load. This is the offered load. Offered load is what? Is the aggregate load that all TCP sources are what? Dump. Not only one of them, all of them. Are you following me on that? All of them are dumping into the network. That's the offered load, carried load. The carried load, or what is referred to as what? Throughput. You see that the relationship is as follows. At the beginning, it's almost a what? A straight line. Why? Because the network is what? Underutilized, which means what we have is available. So whatever you send, it's, the packets will be what? Will be delivered. Notice by packets will be lost or will be dropped mostly because of what? Congestion. What? Errors. This is not a wireless network. This is a what? The internet we are talking about. The transmit all what? Fiber. And the fiber is of extremely excellent. So if a packet gets dropped, most of the time, it's the reason is what? Is that the network is getting what? Congestion. The router does not have what? Does not have space or place in the buffer. This is not the same as what? In wireless network that we'll talk about later on. In wireless, the biggest reason that a packet is what? Is lost or destroyed is because of what? Collisions. Why? Because the medium is what? Is shared. In here, the medium is what? Is a slotted for all fiber. Are you following me on that? So in wireless, the reason, most of the time, the reason for packets to be lost to what? Transmission errors, or due to what? Due to contention, collisions, and so on and so forth. Like in, if you remember the Wi-Fi, the 802.11, can two nodes transmit at the same time? What will happen if they transmit at the same time? There will be collision. Are you following on that? Major reason for the losses of packets is collisions. Whereas in this, we are talking about the internet here. This is not wireless stuff. Did you get it? So at the beginning, the network is what? The network is underutilized. As you increase the offered load, the throughput will also increase. Everything is okay. As you increase what? As you increase the offered load. By the way, queuing terminology, this is when what? When the land is approaching what? New. When land, what does it mean? It means row is approaching what? One. For the single server case. For the multiple server case, what does it mean? When lambda approaches what? CMU. When lambda, the row will approach what? Row approach one, results what? Goes high. This one is not showing you the delay. So if you want to see the delay on the same graph, it's like the delay. Of course, the delay will always what? Will always be increasing. Delay can only go up. Clear? Okay. So as you approach this point, the delay will go where? The delay will go to what? To infinity. Are you following me? By the way, if the packet gets dropped, the delay is equal to what? Why? Because if the packet gets dropped, it will never be delivered. Clear? But if the packet gets buffered for a long period of time, the delay will just simply what? Increase. Clear? Now, at that time, what happens? What happens is that you have reached the knee. This one is called the knee, your knee. It looks like your knee. And then what happens in here? As the offered load increases, the throughput will always what? Go down. When the sender is supposed to what? To slow down. The sender is supposed to what? Stop even. Why? He keep retransmission. Why is he retransmitting? He is retransmitting because what? He did not receive acknowledgement from the... He retransmit. The aggregate offered load will even be what? More. Because then you in new packets and you are retransmitting old packets. The situation will become even what? So in this case, when this happens, the sender needs to what? Needs to slow down. Okay. Now, how do we do this? Oh, sorry. How do we solve this problem? One point is what? Just adding bandwidth is like putting a Band-Aid on a wound. You hurt yourself. You put a band, it's just a temporary solution. It's just a temporary solution. And it costs a lot of money to add the bandwidth. But explain to me why adding bandwidth results in relief of congestion. Relief of congestion if you are adding bandwidth. If you are adding bandwidth, what does that mean? It means the transmission will go what? Will go down. What is the transmission time equal to? Transmission time of a packet equal to? The length of the packet divided by what? The bandwidth. If you increase the bandwidth, the transmission will go down, which means what? The waiting time in the buffer will go also what? The wait that much. Why? Because the server is working what? It's working very fast. Did you get this or not? It's working very fast. So increasing the bandwidth or increasing the what? Buffer size. What does increasing the buffer size mean? You avoid dropping packets. You are delaying. Which one is better? Delaying packets or from the user point of view? From the user point of view, which one is better? Or dropping packets? Delaying packets is better. Why? Because dropping packets requires you to what? Those. Delaying, it means what? You just need to tolerate what? A little bit of delay. Now, to do that, you need to increase the what? You need to increase the buffer size. Clear? Okay. Now, but as I told you, you need to have mechanisms for what? Controlling your congestion. You trap all the mechanisms that we studied earlier for the quality of services in terms of what? Traffic policing, traffic isolation. See, if you do not isolate traffic, listen to me, if you do not, is it possible that many TCP sessions share the same link? And if they link, they are sharing also the same buffer. And if one of the TCP sources is abusing or sending too many packets, everybody will what? Everybody will suffer. So when we talked about what isolation of the semester is establishing a what? A logical buffer for each flow so that source begin transmitting packets more than it was supposed to. Only that source will what? Will suffer. Okay. So, you know, this is not enough. It's not enough. Adding bandwidth, we need what? We need mechanism to control and manage the traffic as needed. Okay, to provide fairness and to provide quality. Clear? Okay, we need to establish policies. We need to establish some notification, flow and congestion control, and so on and so forth. Buffer management, the scheduling of these things, we need to take them into account. Now, in TCP, which is again, as I told you, end-to-end, they needed to what? Define another window. So now, what do I have? I have the congestion window, and this is what? The advertised one. To tell me what is the effective window size at the receiver. Effective window, sorry, at where? At center. What is it? It's the maximum of these, which is what? Which is the minimum of these, minus, of course, what? This, did we see this a moment ago? What is this? The last byte sent minus the last byte acknowledged. What did it determine? Those are the bytes, what? Send, but not yet acknowledged. And you take the maximum of these two. Okay, so if sorry, you take the minimum of these two and you put it here. So if the minimum is WA will be here. And the problem will become what? If WA is less than WC, what is the problem? A flow control problem. But if WC is less than WA, then it's a what? It's a clear, it's a congestion problem. Are you following me or not? Okay. The difference between them is that the sender know this. He only need to what? He need to implicitly guess it. Clear? He need to implicitly. Okay. Now, managing the congestion window is what? Is that you need to decrease. You need to decrease the window size. You need to decrease the window receives high congestion and increase the window when TCP perceives that there is not much. Okay. Now, this is how it started, TCP. It started using, a technique called what? AI. The slow start was not there at the beginning. The slow start, remember the slow start? Was not there at the procedure was called what? AIMD, which is what? Additive increase, multiplicative. What was this? Additive increase, multiplicative decrease. Let's see if you can help me. In the additive multiplicative increase, the sender will send what? Will set up his window by what? One max. We call it what? MSS. MSS stands for what? Maximum size. By the way, that's another parameter that the client negotiate during the what? The handshaking process. This business about the handshaking, when we studied, say what? It's an agreement to start what? To synchronize the sequence numbers. But in reality, they need to go into negotiation. One of them that we just talked about, which is what? Which is the scaling factor. Another one is what? Sorry. What is the what? Maximum segment size. What is the maximum segment size? And it is up to the what? To the server to decide the final thing. The client, the server has the last word. Last word means what? They decide what do you want. Okay. Go into the AIMD. This is how it started. This is how it started. You send what? You set with what? One maximum segment size. What does maximum segment size? Let's assume the MSS is 1 kilobyte. What does it mean? It means the sender is going to be transmitting 1,000 bytes. No more time. I am assuming that the minimum of these two, which one am I assuming? That the minimum of these two is who? Is WA. Did you get this or not? Because I'm talking about what? Congestion right now. Clear? Okay. In the midterm, I will give you a problem where I will give you both of these so that you can what? You can try how do you manage your window size? As I will show you in just a second. Okay. MD, AIMD. You send what? One maximum segment size. You got a what? Within RTT. What is that an indication of? What is that an indication of? Indication that the network is not congested. You increase your window size by how much? By 1. You transmit how many? Max 2. You got acknowledgement for both. Notice this diagram, it shows the acknowledgements as what? Separate acknowledgement. But keep in mind that TCP allows cumulative acknowledgement. Even if it is a cumulative acknowledgement, it is still the receiver is acknowledging 2 segments. What do? You increase your window size by what? 1. So in other words, this technique, what are you increasing your window size? You are increasing your window size for every what? RTT. For every RTT. Not for every what? Segment. But for what? Did you get my point or not? Yes or no? Okay, good. So, I transmit to 3. You got to 3 acknowledgement. You transmit 4. You receive 4 acknowledgement. All of this, by the way, an indication that the network is what? Is not heavily congested. It's not heavily receiving the acknowledgement. Now, what happens? What happens? A timeout occur. What do you do? Look here. Is it linear increase? That's, is it additive increase? It is linear. Excuse me. Is it additive increase? You are additively increasing? Yes? Okay. What happened? What happened? Congestion occurred. The timeout occurred. What do? You decrease your window to what? To 1/2 the last what? To 1/2 the last value. What does it mean? If the last window, let's assume the last window was, what is it here? I cannot read it. 30 window was what? 30. What is your new window? New window is what? It's 50. Did you get this or not? No response. Did you get this or not? You drop it to 50, and then what? You repeat the process. Clear so far? Okay. What was? Can you zoom back, please, a little bit? Thank you. Okay. Did you understand this question? The increment of the increase is S multiplied by what? MSS divided by what? The congestion window. What does that mean? What does that mean? And in here, how many did you send? 2 MSSs. Yes? It will be what? 2. The congestion window was what? Was 2. So you add by what? Are you following me or not? You are going to increment your window. One more time. When I say your, who's your? The sender. This is the sender. Your window size. By 1 MSS for every what? For every what? For every acknowledgement received. But for every what? Every RTT. Did you get this or not? Every RTT. By the way, RTT is not a fixed number. It's a random variable. Are you following or not? So you need to wait. What is the value of the RTT and set yours? We'll see in just a second accordingly. Clear? Okay. So this one here again. 4, you get 4. 6, 6, and so on. You are going to get what behavior? What do we call this behavior? You will get the sawtooth behavior. Did you get my point or not? No response. Did you get this or not? Was the original intent of TCP. A user started why it is complaining. Why they are complaining? They are complaining because if the network tested, it will take you long time to what? To build up your rate. Who's your? It's the sender rate. It will take you longer time to what? To build up your rate. The goal of what? The goal of TCP is to what? Force. Trying to figure out, TCP is trying to figure out what is the what? What is the highest thing that I get away with me is what? I can transmit at that rate, at higher rate. Did you get this or not? Introduced a new mechanism, which is called what? A slow start mechanism. A slow start. When we say slow start, it means that you start with sending how many segments? Why? Because you have no idea whether the network is already what? Congested or not. You want to what? Go ahead and send many segments and then you was what? Was congested. Clear? So you send what? One segment. You got a what? An acknowledgement. Every time you get an acknowledgement, you double your what? You double your window size. The increase in the window size is based on how many what? How many segments that are acknowledged rather than on every RTT. So here he got acknowledgement. What did he increase his window? To acknowledgement for 2. What did he increase the window? 4. Why? Why is this 4? Where did this 4 came from? And here 2. Yes? He got how many acknowledgement? 2 acknowledgement, which means what? 2 segments. For every segment, he will double the what? He will double the window. Did you get this or not? That for every acknowledgement, he will increase his window by what? 1. How many acknowledgement did he receive? 2. So he what? 4. He received 4. What will he do? He is not there. Next, he will send how many? 8. Are you following me or not? Yes? Is he aggressive? He is getting aggressive. So in here, the sender will increase his window by 1 MSS for every what? Segment acknowledged. Again, I want you to, one more time, I want you to compare this with this statement. Side by side. This one, the sender will increment or will increase 1 MSS for every segment acknowledged, whereas this one, he will increase his window size by for every what? For every RTT. So during the RTT, if he receives, he will increment his window by what? Just 1. Are you following me? It's per RTT, whereas in here it's per what? Per segment, sorry, per acknowledgement. Every acknowledgement, you double your window. Clear? Okay. So what did they do? So this is what we have. If you look at this, you have seen this diagram before. Again, this is the art, and this is the what? Congestion window. You start at 1, then becomes what? 2, what? 4. Are you following me or not? Increasing. Every RTT, this is what? 1, this is what? 2, this is what? RTT. So this one, at the beginning of what RTT, this is the end of the first RTT. And the second, the beginning of the second RTT. And so on. So now, next thing they said is the following. Is that, is this one going to go on and on and on forever? Notice my point of view. The user point of view is what? Is that it would like to continue that way. Do you agree? The sender is getting what? More aggressive. He is getting what? All his segments are being what? Transmitted and delivered. So they said, let's set up a threshold. Let's set up a threshold. And what? After we reach that threshold, go to the ARMD. In other words, slow the rate. Which one is a higher rate? This one? The rate means what? The slope. The slope. Which one is higher? This or this? This one is. So the next question is what? How do we set the threshold? How do we set the threshold? So once you reach a certain threshold, the threshold is what? 8. Then what do? You start what? Going linear. My point or not? Yes or no? This is what they refer to it as what? Congestion avoidance phase. It's not a congestion avoidance thing. You are still increasing the rate of what? your transmission. Slow down the increase in the rate. You slow down the increase in the rate. Clear? You are. Now, most implementations actually of the TCP, the initial slow start threshold, they make it what? They make it too high. What does that mean? Make it too high. It means what? They allow the sender to keep in which phase? The slow start phase until what? Until congestion occur. And then what will happen is what? What will happen is that you are going to set the new threshold. And what is the new threshold? Is the old window divided by what? Divided by 2. Did you get this? Yes or no? Oh, now, so what did they say? The sender is going to be aggressively what? Sending. If congestion occur, we need what? More severely. Do you understand? See this one here? What happened in here? If congestion, where is the window size going to be? The window size will be divided in what? In half. In here, if the sending at a what? At an exponential rate, they said what? We need to put what? Punishment, a bigger punishment, if what? If timeout occurs. This or not? What was the bigger punishment? Let's see if you remember. It's if this, and suddenly what? Congestion did occur. What do? You all the way down to what? 1. Is this bigger punishment than this? The punishment is this one. Hey, this one is bigger than this one. Did you understand what I just said? No, now it's like what? It's like I'm telling you that if who's you? It's the TCP sender. If you decided to keep increasing your initially, and if a congestion occurred, you are going to drop it all the way to what? All the way to W equal to 1. Then, by the way, then what do you do? What do you do next? You do what? You go. Yes? Start this slow. What is the new threshold? How did you get the new threshold? The new threshold is the old window divided by what? And once you reach this, you end up with what? This. Clear? Oh. So, again, this is the slow start. Okay, so in this slow start, you start by setting your congestion window WC to 1, which is the maximum segment. The receiver, when the sender receives an acknowledgement, it increases window by 2 segments. If it receives acknowledgement for these 2 before the timeout expires, it increases its window to what? To 4, and so on and so forth. All of these is referred to as what phase. Again, one more time, the meaning of the word slow start is a little bit what? Misleading, because really aggressively increasing the rate of its transmission. Clear? Okay. Now, phase 2, once the congestion window reaches a threshold value, that threshold value is called what? The SS. Then what happens? He get into the AIMD, which is the multiplicative decrease. He will increase his window by what? 1 for every what? RTT, not for every acknowledgement. For every RTT goes by, he will increase his window by what? By 1. Phase 3, once congestion occur, the congestion window stops increasing when the client TCP detect that the network is congested. How did he detect it? If the acknowledgement does not arrive before the timeout. Before the timeout. Clear? Okay. Can we set the timeout? But if you set the timeout too long, it means what? It means that you are not, see, you do not get acknowledged. If you set your timeout long, and if you do not get acknowledgement in the, what will happen? What will happen is that you keep waiting for the what? Waiting for the acknowledgement to come, yes? Which means what? You are underutilizing the what? The resources in the network. If you set your time, it means what? You are panicking quickly. Panicking quickly means what? You are not even giving the chance for the receiver to watch your segments. Clear? Okay. So you set the new threshold to 1/2 the old. You go into what? You go into the AIMD like a scene here. So this is what? And then this one what? Increasing linearly. What happened here? Can you tell me? Remember what I told you a moment ago. This point is set at the beginning very high. In other words, think about it as what? Set to infinity. Allow the sender to keep what? To keep in the slow start until what? Until congestion. Clear? Okay. Then in here, for example, in this diagram, congestion occurred here, but will drop all the way to 1. Then you start a congestion and increases linearly. This is what as the Tahoe implementation. We have 450. This is called Tahoe implementation. I'll explain that to you in just a second. Clear? Okay, good. Now, the fast retransmission. Fast retransmission. What does fast retransmission mean? I've taken this in 450. Did just a quick review. Let's see if you can help me here. Here he is sending the packets, packet 1, packet 2. He got acknowledgement. This one got lost. Remember, by the way, TCP is a reliable protocol, which means what he needs when he deliver the bytes to application, those bytes has to be in what? In order. So what did he do? This one got lost. Okay. Why did this one get lost? It got lost for different what? For different reasons. One of the reasons is what? Clear? Get lost. Now, he sent another one. What happened? This one, this one is what? Is out of order. What will he do? He will buffer this one, yes, but the old acknowledgement. What was the old acknowledgement? What was the old acknowledgement? Acknowledgement 2. Acknowledgement 2. Did you get this or not? Yes or no? Notice, by the way, if the receiver is in go back N strategy, do you remember the go back N? Go back N, 450. What will he do to this packet? He will drop it. Are you following me? Because in go back N, the receiver is not willing to buffer any packet that is out of order. Most implementation of TCP uses what? Uses selective repeat. In a selective repeat, ARQ is willing to what? To buffer packets that are what? That are out of order. Clear? Acknowledgement. The sender is what? Sending a packet number what? 5. Packet number what? 6. What? Out of order. Yes? He will buffer them, but he repeats the what? Acknowledgement. Did he repeat the acknowledgement? At this point in time, what did the sender receive? He received 3 duplicate acknowledgements. Where are the duplicate acknowledgements? This one, and this one. These are 3 duplicate acknowledgements that already what? Acknowledged. That's the original one. That's the original one, and these are the what? What does he do? He does not wait until the timeout what? Occur. He will what? Retransmit packet. Packet number 3. He retransmit packet number 3. Notice, by the way, misleading. Why is it misleading? It tells you packet number 3, packet number 5. You remember the packet, what is being numbered are what? Are the segments. Did you get this or not? Yes or no? And this a little bit, I blame the authors. The packet 1, packet 2, packet 3, these are what? These are all clear? But when we talk about the network does not see the segment. The segment happens to be where? Clear? Clear? Okay. We needed for this fast retransmission. Again, do you answer what fast retransmission means? Avoid waiting and timeout for this. Packet 3, where was the timeout? The timeout was somewhere in here. Yes? But it is telling you the sender. You are telling the sender, don't wait until what? Until this one in here, because you already received what? 3 duplicate acknowledgements. Are you following me or not? Okay. Now, they're going to treat how we are going to differentiate this case from a timeout mechanism case. In this case, is the congestion situation as bad as the timeout mechanism or not as bad? Not as bad. Why? Let's see the indication why it is not as bad. 3 segments out of order, which means what? It got through the network. Remember, the receiver is not going to send acknowledgement if it did not receive segments that are what? It must receive segments out of order before it duplicates the previous acknowledgement. If it got it through, it's so badly congested? It's not so badly congested. In addition to the what? Segments out of order, the acknowledgement also will what? The acknowledgement also got through the network. Yes or no? So means what? The situation is not as bad as it seems. Clear? So I will show you this in just a second. They introduce a mechanism which is called what? Fast recovery. What are you trying to recover? When we say what are you trying to recover? You are trying to recover your window size, your last window size. The fast recovery, which was introduced in Reno, what? When a timeout occur, when the 3 duplicate acknowledgement occur, not a timeout. 3 duplicates. Don't punish yourself all the way to what? 1. Go all the way down to what? Of the last window size and proceed with your what? AIMD. Proceed with without going through the what? Without going through the slow start again. Did you? Yes or no? Without going through your slow start again, reduce your window to 1/2. Not the 1/2 the old threshold, but the 1/2 the old window. Are you following that? Where is this in this diagram? The old window was what? 12. What is the new threshold? The new threshold is 6. The old threshold is what? 8. So now, okay, and you start what? You start. Now, when in this example, when are you recovering old window? After how many RTT? You are recovering your old window. Your old window was what? 12. How many RTT? 2 RTT, 3, 4, 5, 6. 6 RTT to recover your old what? Your old window. In here, how long will it take you to recover the old window? 1, 3, 4, 5, 6. Not yet. Not yet. 7, 8. It will take you what? 8 RTT to recover old window. Did you get this or not? That mechanism, they refer to it as what? They refer to it as a fast recovery, the fast recovery mechanism. The fast recovery mechanism was introduced Reno implementation. In the Reno implementation, it was what? It was now, let me review the Tahoe state transition. Again, we have seen this in 450. I just cut them. See if you remember. You set up your what? Your window by 1 with the threshold. You set the threshold and your window is 1. You start with the slow start. If you receive what? Acknowledgement, increment your window by what? 1. For every what? For every acknowledgement. Not for every acknowledgement, you increment your window by what? By 1. Okay. If a timeout occurs, by the way, and you keep in here. Yes? If a what? Could you receive 3 duplicate acknowledgement in the slow start? Which of course you can. Are you following me or not? What do? You set your congestion window, timeout or what? 3 duplicate acknowledgement. 3 duplicate acknowledgement. If you are in the what? In the slow start. Remember, this is the transition diagram of Tahoe. Tahoe does not do what? The fast recovery. So it treats both of them the same way. So what do you threshold to what? When you have the congestion window, the old congestion window, and your new congestion window is what? Is 1. Now, to exceed the threshold, what do you go? You go to the AIMD. This is the AIMD. Now, in AIMD, you increase your window by what? By what? By 1 for RTT. By 1 for every what? RTT. Which means what? You are increasing by what? 1 over what? Congestion window. Congestion window means what? If you transmitted 5 segments in a window, then you will add what? You will increment it by what? If you receive 5 acknowledgements, you increment your window by how much? By 1. Did you get this or not? Yes or no? Oh. And if a timeout occur or duplicate acknowledgement occur, you are going to go back to here and you send it to 1. This is Tahoe. In Tahoe, there is no what? No recovery. No fast recovery phase. I already explained this one to you. This is a fast recovery phase. Let's see if you can help me here. This is the what? This is the state transition diagram with Reno. Again, you slow again, the same thing. However, what is the difference between this one and this? Look at this and look at this. All of these, by the way, state diagrams, you will take it in CS. How many of you have taken this class already? Did you take this state transition diagram? What about it? State transition. Once you get any topic that has to do with the state, you take it in the what? In the computer science department. They like this state transition diagram because that is like a flow chart. That is like a flow chart, how you write your code based on the state transition diagram. Okay, let's win this one, this one. In this one, in Tahoe, when you are in the slow start and the 3 duplicate acknowledgement occur or a timeout occur, whereas in here, if the timeout occur, you treat it the same way, but acknowledgement occur. If 3 duplicate acknowledgements occur, you are going to go into the what? Into the fast recovery, which means going to what? You are going to set up your what? You are going to set up your threshold into what? Congestion window. And you set your window by SS threshold. Where is this +3 came from? Can you +3? For those of you who take 450 with me, you should remember this. But for those of you who not, I don't know. Add the 3 here. He added the 3 because what? Because he what? There were already what? Acknowledgement that he received. He is assuming, the sender is assuming that were received what? Were received with no errors. Are you following me or not? Which means what? The receiver is going to eventually. You follow me or not? So he is able to increase his window by 3 to get into the fast recovery mode. In the fast recovery mode, whenever he receives duplicate acknowledgement is what? It's still what? He is still getting duplicate acknowledgement. He will only increase his window by what? By increase his window by 1. But once he receives a new acknowledgement arrived into the congestion avoidance phase, which is this one. Which is this one. Sorry, which is this one. Clear? Okay, good. Now, this is an example, again, of TCP. By the way, these diagrams are reading, again, from the author's point of view. Why? Because it gives the impression that this one is going at the same RTT. You are going to modify your window beginning what? The next RTT. Did you get this or not? See this line? This line is supposed to be like this. Did you get this or not? Yes or no? This looks like what? It looks like you are transmitting at the same RTT. This is the next RTT. But it's easier to sketch the diagram like this. Okay, so this is at the beginning, slow start. What happened here? A congestion timeout occurred. Why? How do we know that it's timeout occurred? Because what?
The time
you
is
start
18
the slow
o'clock.
start. Then you reach the, where is that threshold? 4. Why? The timeout occurred at where? So the new threshold is 4. Here. Tell me what happened here. Tell me what happened here. Look at the diagram and tell me what happened here. And here is 3 duplicate acknowledgements were received. What is at what point? 12. Yes? What is the new threshold? 6. And you add to it what? 3. To take into account that 3 segments were already received. No, they were not acknowledged yet. They were only what? Received. They were not acknowledged of order, but they were received. How does the sender know that they were received? Because here, duplicate acknowledgement. The sender does not, the receiver does not send duplicate acknowledgement and leaves segments that are what? Out of order. So the sender knows that these segments that were received. So he set what? He set his window to what? 9. One more time. Explain to me where the 9 came. It's 9 is what? Is 6, which is the new threshold. Yes? Plus what? 3. Tell me what is happening here. What is happening here is that he is still receiving what? Duplicate. Are you following me or not? So he keeps increasing the window. Are you following me or not? Okay. What happened here? Tell me what happened here. What happened here is that what? He receives a new acknowledgement. What does he do? He settled to the old what? 6. Why? If he received, what does that mean? It means those 3 segments that were received out of were what? Were now acknowledged because the sender receives a new acknowledgement, not anymore. Clear? So he needs to remove those 3 from his window. And he set his window to the what? To the old. Start with the what? With the AM. Clear? Clear? We saw this one in 450. Now, one final thing before I leave darts. All of this, we were assuming that the problem is what? Congestion control. I will give you what? I will give you a value for what? Excuse me. Value for what? WA. Did you understand what I just said or not? So that you need to keep track of which one is the what? Is the minimum of the 2. Is it the receiver advertised window? The what? Congestion window. Let's assume I give you WA equal to what? Clear? How will this one change? How will this one change? It will change as follows. 1, 4, nothing happened. Nothing happened. No timeout. Yes? But what do you... Horizontal. Why? You cannot go to what? 8, because the receiver is telling you you cannot go 4. the problem becomes a what? A flow control rather than a what? Congestion control problem. And I will give you that in the midterm. Did you get my point or not? Okay, good. So, careful. Okay. Now, one final thing before we leave this set of, which is what? Which is the thing that we call the global synchronization. Now, listen to me. Those TCP sessions that are sharing the same link, are they synchronized? Are they synchronized? The TCP sessions, sources, users, your session and my session. Of course they are not synchronized. Everybody is working separately. Did you understand what I just or not? However, look in the operation, assuming that they are sharing the same buffer. What does it mean? What does it mean? You did not establish what? Separate buffers for each one of them. What will happen if the network gets congested? The best effort model, which drop policy, he is using the tail drop policy. Tail drop policy means what? All the packets end will get what? Will it get dropped first because there is no space to put them. Yes? What happens? They will go to the what? All, who's all? All the sessions. They will all go to the what? The slow start. Yes? As if they were what? Synchronized. But because their timeout has what? Expired, all of them will go. See, they were here, they go what? Here. Did you get this or not? Yes or no? And then they start raising their what? Their rate exponential. Now when they go here, this is the maximum utilization. They are going to be what? Operating and the what? Maximum utilization. What does that imply? What does that imply? The resources of the network used efficiently. Did you get this point or not? Yes or no? As if they... What is our goal? Our goal is only to punish those sources that are what? Using the network, which means they are the only one which will start what? The others can what? Keep continue. Do you understand that or not? Keep continue. And if they keep continue, the aggregate average rate will be what? Will be higher than the minimum. Did you get my point or not? All the what? The global synchronization problem. When TCP flows experience one or more packet drops, they all go into the slow start phase. The traffic load on the network drops abruptly. Abruptly, because all the sources are going to go what? Are going to go down immediately. Clear? All flow starts to increase their rates at the same time, as if they were actually synchronized. Aggregate traffic increase again to the maximum rate, congestion occur again, the tail drop occur, and we repeat the whole thing. Are you getting a sawtooth? You are getting a sawtooth, but because it's what? Slow start. Did you understand that or not? It's not the same as what? As the one that I don't know where I put it. In any case, exactly a sawtooth. Are you following why? Because these are what? Are exponentially started. Now, to avoid this again, as I told you, you need to create what? You need to isolate the flows. You need to isolate the flows. Everyone, they have their own buffer. Now, finally, the retransmission policy, TCP performs again end-to-end. Does not employ negative acknowledgement. TCP does not employ negative acknowledgement. Clear? Does not employ. Now, as we discussed, it depends on the implicit congestion notification and uses an adaptive timeout, RTO. It's an adaptive retransmission timeout. This timer depends on the observation of the acknowledgement delay. So what they do is that they do the following. They estimate, first of all, the RTT. They are going to set their timeout mechanism based on their estimate value of the RTT. Keep in mind, the RTO, the retransmission timeout, and the RTT. Do we agree? Do we agree? Okay. Is the RTT changing? Which means what? He needs to adapt, the sender needs RTO, which is the retransmission timeout, based on the estimated value of the RTT. When you do the of RTT, you don't look at what, by the way, how do you calculate RTT? You mark the time that you send the packet. Yes or no? When you receive the acknowledgement, you notice the time that you receive the acknowledgement. The difference between them is what? Did you get this or not? But when you measure the RTT, you don't measure it on a what? On a sample, because the situation changes what? drastically. You need to what? You need to have what is known as a what? Running average is what? The smooth, they call the smooth RTT. Smooth RTT at K plus 1, K plus 1, K plus 1 is what? Is, I'll explain to you the beta in just a second. Is the smooth R time what? K, which covers what? Which covers all the previous ones. Beta plus what? 1 minus beta times what? RTT, this is what? The RTT of which sample? Of the K plus 1 samples. Did you get this or not? Okay, you scale it. Now, usually they use what? They use beta such that this effect or more weight than what? Than this one here. Are you following that? Because the situation is changing what? Drastically. Now, once you estimate this, by the way, it becomes like this. If you open it, it becomes like this. You notice, by the way, at K plus 1, what does it depend? On the what? The previous sample, the previous sample, the previous sample, all the way to the first sample. Did you get my point or not? So you are averaging. Now, once you what? Once you estimate, then RTO means what? Your transmission timeout is set to be what? S at K plus 1 plus some alpha, some weighting factor, times what? SDEV. SDEV stands the standard deviation at what time? At time K plus 1. Standard deviation of who? Of who? Of the RTT. The standard. Remember, RTT is a what? Is a random variable. Did you get this or not? The standard deviation at K plus 1. So you add this one with this one to get what? To get the estimate of RTO. If you see this, the RTT variation. Is it varying so fast? It's varying so fast. Some what short. Sometimes the RTT is what? Is long. Did you get this or not? Yeah. There is also another situation. Let me just quickly show it to you so that you understand what I'm talking about. Let's assume that you send a packet. You send a packet. Send the segment, segment. And you get an acknowledgement after the timeout expires. Timeout expires, you retransmitted the segment. You receive acknowledgement. Which RTT are we talking about? He will getting confused. Is the RTT from here to here? The RTT from here to here? Did you get my point or not? He doesn't know which one is the RTT. They suggest what? You don't take into account the RTT fence that are actually what? Retransmission. You lost me here? Did you lose me? Here. What is this? This is the timeout. Timeout occurred. He retransmitted the segment. He then receives acknowledgement. First of all, is this a retransmission of this? This one. Is it retransmission of this? Acknowledgement. How would you calculate RTT? In this example, how do you calculate the RTT? The sender will assume that this is the RTT. Did you get this or not? But in reality, was it? From here to here. So in the calculations of the RTO, in your calculations of the RTO, select any what? Any measurement from those segments that you are what? Because their measurements for the RTT is not what? Reliable. It's not reliable. It causes what? It causes a problem. Clear? No response. And finally, the last set of charts. They introduce now an EP. They call it what? TCP Vegas. By the way, there are many. There is TCP Westwood. There is Tucson. Are you following or not? TCP is all versions written in what? In TCP Vegas, RTT, based on the RTT, the sender will what? Will either increase his window or reduce his window. Based on the RTT, not based on a timeout or something like that. So if the RTT is long, what does he do to his window? His window decreases. That the RTT is what? Short, he will increase his what? His window. So let's see, source tries to match the available bandwidth exactly. TCP source maintains what is known as what? The base RTT. The RTT when the flow is not congested. Think about this as a what? Reference as RTT when the what? When the network is not congested. Clear? That's the base RTT. Typically the minimum of all RTTs observed. It uses this value to determine whether congestion is being exposed. Computes the expected rate, which is what? The congestion window divided by what? The base RTT. That's it. congestion window divided by what? The base RTT. Congestion window means what? How many or how many maximum segment size? It is what? Ascending. That's the average rate. The actual rate also is a number of bytes transmitted during the RTT of a tagged segment. Tagged segments means what? The segment that is being what? Perceived to be causing congestion. Thank you. If the what? If the difference is less than alpha, the difference between what? The and the what? The base RTT, TCP will increase congestion window linearly. If the difference is greater than what? Some other threshold, beta, difference between who? Difference between actual RTT and the what? The base RTT. If the difference is greater than beta, then he decreases the window linearly. If the difference is between this threshold and this threshold, he leaves the window as is. Clear? Clear? Okay, this is called the Vegas test. Clear? Okay, finally we are done with this set of notes. God, it took us forever. Okay, next, looking at. Did you get this set of notes? This will be included in the midterm as well. So both sets of notes will be included in the midterm. Be careful. Now let's look at what? Let's look at the switching fabric. Inside the routers. Inside the routers, there is a what? There is a switch. Clear? There is a switch. This is the function of a switch. This is an N by N switch. What do I call this switch? This switch, square switch. Square switch means what? The number of inputs, the number of outputs are what? Are the same. A square switch. Of course not, as we will see in just a second. If this one, then we call it what? An expand. But if this one is more than this one, we call it a what? A concentrating switch. Concentrating number of inputs, low number of outputs. Expanding means what? The other way around. A low number of outputs. Clear? Okay. But let's look at, first of all, at an end. The function of a switch is to take the traffic from an appropriate or for a particular input port to a port based on some identification. Based on some identification. When we, this coming week, on MPLS. MPLS stands for what? Multi-protocol label switching. That the switching is done based on a what? Label. But in packet switching, here to here is based on what? It's based on the destination IP address. So it depends on whether the switch is a packet switch or an MPLS type switch. Clear? So based on some identification, to take it from what? Going to take it from an incoming port to an outgoing port. This is a generic switch, means what? Doesn't matter which type it is. You have what? You have the incoming ports. There is every one of them. This is a processor, a microprocessor in it that will do what? That will do functionality. By the way, when you come in here, which functionality comes first in this processor? It incoming into a router, it will go through what? In other words, this one is divided into what? Three. The first one is what? The physical layer. The second one is what? The data link layer and the network layer. On the other side, it's the what? Round. Did you get my point or not? Why? Because you are going from what? One router to a what? Remember the layered architecture. When you are sending, you go what? Top, bottom. When you are receiving, you go what? Bottom to top. So when you are receiving, this one will go which layer? The physical layer, data link layer, and what? Network layer. When you are sending, you go network layer, data link layer, and physical layer. So we have a processors at what? At the input port, output port, and then we do have a control processor that will control the connectivity within the what? Switching network or the switching fabric. This is what we are interested in here. Clear? What goes in here? Oh, this is again, as I told you, from the link layer. This is the table, the lookup table. The lookup table in this case here, by the way, is based on what? Based on circuit identification. If you are using what? If you are using, for example, ATM, or it's what? A routing table. You go and okay. I'll continue next time. Clear? Okay. Continue next time. Okay. Don't forget, you do have a graded homework and drop by to pick it up. Drop by to pick it up today. So make sure to submit it.